thank you. And thank you to Bruno as well for the previous talk. It's a lot of good background for this talk. So yeah, this is work I did with my advisor Tim Shear, and generic constructors and eliminators from descriptions. And it's basically like type theory as an embedded DSL. So really, you could call it generic type theory from descriptions because there's one part that the paper doesn't talk about that I'll talk about in these slides, which is also generic type formers, not just the constructors and eliminators. So the motivation for this is that you can define data types using this technology called descriptions that originally was from the General Art of Levitation paper that appeared in ICFP a while back. And with descriptions, you can basically do generic programming over sort of all user-definable types within a dependent type language, where all means, well, all the types that the descriptions are capable of encoding. This tends to be a really large class, including type families. And you can even do like induction recursion, a lot of different types. And the one sort of disadvantage of this approach is if you want to encode your data types like this, then you kind of need to understand the low-level encoding to be able to work with data types defined using these descriptions. And instead, kind of users of type theory are already familiar with the standard interface of, when you declare a data type, the type formation rule and the constructors or the introduction rules and the eliminator or elimination rules kind of have the standard interface that type theorists already know and understand. So instead of making them learn what the encoding sort of elaborates to, you can, using generic programming, actually provide sort of type theory as a DSL for working with these described types, but you still get the benefits of the described types, which is that you can write generic functions as well. This is, so basically with descriptions, instead of having a traditional open type theory where when you have a data type declaration, it extends the theory with sort of axioms, maybe with some computation rules for the type formers, type formation constructors and eliminators. That's kind of the traditional way of doing things. And then within dependent type theory, you can write generic programs, for example, like a marshalling generic function. So you define some subset of types U, and then interpret the, so U basically represents codes for a subset of types, and then EL translates each code of a type into the actual types. Maybe this is like the code of bools and the code of strings, and this is like the actual bool and the actual string. And if you pattern match on U first, then that determines the actual value in the language so that you can write a generic function. And this is sort of a traditional way of doing generic programming within a dependent type language. And the limitation is that it's over a subset of types. So with a closed type theory using descriptions, when a user writes a data declaration, instead you can translate the data declaration into primitives of an existing theory, so you don't need to extend the existing theory. And now when you do generic programming, you can do generic programming like this, where D is the description, which represents a sort of first-class embedding of data type definitions. And then you can take the fixed point of that definition to get back the actual type it encodes, or something isomorphic to like what you had in mind when you wrote a high-level data type declaration. This is like a traditional in an open type theory. What you might do, you might declare a data type like vectors, and then you have an eliminator for it. And sort of in type theory, when you introduce types, they have this kind of expected interface, right? So like you have the parameters of the type former, and then you have the indices, and then for each constructor, you have the constructor ending at some particular index and taking a bunch of arguments as function arguments, and then ending in some index. And the eliminator starts with parameters, and then you have the motive for the eliminator, and then all the different branches. So the eliminator here is basically the sort of fold algebra for dependent types. And instead of actually extending the theory like we would do in an open type theory, what you do is, the type former actually translates in a closed type theory to a use of the fixed point mu, and the constructor will translate into use of the initial algebra for that fixed point type, and the eliminator will translate into this in, which is sort of like a dependent catamorphism. And these, if you want to use these encoded data types directly, you kind of have to understand the encoding. So instead, what this paper is about is defining these generic functions, form, ing, inject, and elim, that once you partially apply them to a description of the data type that you're encoding, the type signature will match the expected interface that everyone's sort of familiar with from type theory here. So at a high level, you can kind of, the thing in common with everything in this presentation that I'll talk about is that it's, they all sort of convert between the, you kind of have primitives in a F-algebra structure, and you convert them into a fold algebra structure, which is sort of the structure that you kind of expect from type theory. And there's actually more going on than just that, because you also have to encode things like proofs about what the indices of type families are. So it's not just converting between F and fold algebras, but that's a large chunk of it. Okay, so yeah, in the paper I talk about defining ing, the generic constructor, and elim, the generic eliminator. But elim is quite involved to describe, so I'll refer you to the paper for that. And in this talk, I will talk about ing, which is the generic constructor, and pretty easy to explain. And then I'll also add something that's not in the paper called form, which is the generic type former, which doesn't require too much extra complexity. And also, if you've already read the paper, then you can still pay attention and learn something interesting. All right, so, but it's all self-contained. So here's the data type of description. So what you should think about this data type as is a sort of a first-class version of the definition of a data type. Specifically, it's easier to think about these descriptions as encoding the definition of constructors and what arguments the constructors have and what return type the constructor has. So first of all, it's parameterized by some set representing the index. So we're talking about type families here. And second of all, so then there's three different ways that you can construct one of these descriptions. So maybe the most basic or easiest to understand is just a regular argument. So you have a constructor, and the constructor might have an argument. So that argument is going to be of some type. So you indicate what type it is, and then the rest of the description can depend on the value of that type, because we have constructors for dependent types, which along the telescope can depend on the previous constructor arguments. And we can also have a recursive argument, and with a recursive argument, so this is an argument of the type that this description is defining. You can't depend on the type that you're currently defining, at least in this version where you don't have induction recursion. So all you need to provide here is the value of the index, because at every recursive argument you specify a particular index that the recursive argument should be at, and then you describe the rest of the constructor arguments, and finally you end at some index. So when you end the final, when you have no more arguments for your constructor, then the constructor as a whole ends at some particular index indicated by I. So here's an example of using this for defining vectors. So this vect is just an enumeration for the two constructors, nil and cons, like the tags of the constructor names, if you will. And vec C specifies what the description is for each particular tag. So the description for nil, nil doesn't take any arguments, and it ends at the 0 index. So we just say end and then 0. And the description for cons is we require a natural number argument, and then we require an argument of type A of the parameter, and then we require a recursive argument of type n, which depends on the n given previously. And finally, we end in the index successor in that. And sort of using the isomorphism that you can use a dependent pair as a sum, we encode like the sum of all possible descriptions using this arg. So an arg taking a tag, and then for each particular tag, you will construct the description for that tag. So that's how you would encode using these primitives a data type like vector. So like a high-level user declaration would translate into what was on the previous slide. And then there are, so in order to use these, you're going to need to take the fixed point of that description. So in order to do that, we're going to need this function called EL, which translates a description into a concrete type in the language, parameterized by some x, where x represents the recursive position. So basically, you can sort of think about this as an endofunctor where if you partially apply EL to D, then you get back the endofunctor between these families of sets. So for, again, the arguments are maybe the easiest. So for an argument description translates into a product, or a pair with the first argument of the A that we asked for, the type that we asked for, and then the rest of the interpretation can depend on the value of that A. And for a recursive argument, we ask for this X, which again represents the recursive type that we're, or it represents the type that we're currently defining. And we ask for the X at some particular index, J, namely the J that the recursive code encoded. And then again, we ask for the rest of the description interpretation. And finally, we end, so we have all these products, and then we end in this proof here, which is a proof that the J index that we said we were going to end at is actually the I index that this sort of families of sets is currently defined to be. So once we have this EL, this interpretation function, then we can define the fixed point of it by, so basically if you replace in your mind this ELD with F, then this is sort of the regular F algebra based fixed point. So this is kind of like F of mu D, besides the fact that it's for type families, but sort of F of mu D, and then here this would sort of be F instead of D. So now we're going to take a look at how you would construct values using these types and how it differs from how using the primitives differs from sort of the interface that we actually expect. And then we'll drive the constructor to get the interface that we expect. So to get the actual vector type, we just take in a parameter and then apply the fixed point to the description by passing in the parameter A. And if we were sort of interactively constructing a vector of length 1, then using the primitives, we would start with using init, representing the initial algebra, and that's the constructor for the fixed point, init, the initial algebra, or the initial F algebra specifically. And then we would remember the interpretation function interprets everything as sort of products ending in some equality proof. So here, this is going to be a pair, and on the left component, we first indicate what the tag is, and that will determine the description for the rest of the arguments of this constructor. And so what goes into this question mark here is this interpretation function for the the cons constructor, and that evaluates to this pair. So again, it's a pair that first takes a natural number and then takes a vector at that natural number, and finally takes an equality proof that this index better equal the index that was sort of specified in our type up here. So suck0 should equal suck n. So basically, the only valid instance of n here is going to be 0. The important thing to note is that this is not equal to sort of the expected constructor interface. So ing, which I'll be introducing shortly, this is sort of how we would like to use this. So we'd like to say ing and then vector description and pass in the constructor tag that we want, and then have 3 sort of question marks, where the first one is the natural number, the second one is the a, and the last one is the vector. So kind of as a big picture, the difference is if we were going to use the primitive initial algebra, we would have this sort of structure where we have a pair and then all of the arguments ending in some equality proof. And what we want is this sort of curried version of the structure that has the equality proof sort of implicitly instantiated. And that's why it's not strictly just converting between F algebras and fold algebras. There can be extra things that you might want to hide in your DSL, such as like the fact that this equality proofs for the type family indices is actually in the low-level encoding. So if we had this sort of ing, and we could define our regular constructors of type theory by just applying ing to the tag that we want, and then the types of those would be the types that we expect from vanilla type theory, or the open type theory instead of this closed type theory. And then we could use that to construct values in a normal way. Versus constructing the values directly using this using the primitives, where you kind of have to know that okay, this is going to translate to this sort of this product of arguments ending in these equality proofs, where REFL is the constructor for the equality proof at inhabitants or witness. And yeah, so we want to get to this ing. So in order to do that, basically what we'll do is we'll think about, we'll define an uncurried version of EL. So we're going to have this uncurried EL basically represents the initial algebra. So we have a function from the interpretation of the description to some recursive type, which is always going to be instantiated at the fixed point in practice. And instead of having the uncurried version, we'll define sort of a curried EL that computes this sort of a telescope of functions instead of the telescope of pairs. And for the non-recursive types, it can be dependent. For the recursive types, it's not dependent, and it uses the proper index. And for ending, it just uses the proper index. And then it's pretty straightforward to just define the curry EL to go between these things. The important thing is to just recognize what the type signature of this is. So the idea behind this whole paper is basically understanding how to construct using dependent types, right? We're constructing types dynamically that produce the interface of the DSL that we want to actually use instead of the low-level sort of type signatures that our primitives actually encode. And the kind of subtle thing, perhaps, is that we're not just doing currying. We're also, like if we were just doing currying, then this end constructor would actually have this extra equality proof as an argument. So instead of having this equality proof as an argument, we kind of push this I of curry EL prime out into another place, namely the primitive constructor that we're deriving ing. And by doing that, we don't need to ask for this extra equality proof, and this can kind of just be implicit. So we, when doing this sort of DSLs, when doing these sort of DSLs for type theory, we can sort of, we just have to think about what the type signature is that we want to compute. And in this case, we don't want to supply equality proofs in addition to just doing currying. And then defining ing is very straightforward. We just use curry EL and specify for x the initial algebra. So one thing that was kind of not mentioned in the paper is like, what if we have multiple parameters, or what if we have multiple indices? Like if we're encoding like this tree, which has, which basically counts the number of A's or number of B's at the leaves. So we have, leaf 1 has like 1A, leaf 2 has 1B, and then branch sums up the A's and B's. Well, we would actually encode this by, because def just takes a single set, we would have to take a product of these two index types in order to encode this. And you don't really have to stare very hard to try to read how to encode this, but the important thing is just knowing that because the indices are just a set instead of some first-class structure like descriptions are, the generic functions like ing can't actually do anything specifically for the indices. Like, it doesn't know about the indices. So the sort of implication about that is I can't just say like leaf 1 is equal to ing leaf 1, or is equal to ing tree D leaf 1D, because tree D does not encode what the parameters are or what the indices are. So in this case, I have to pass in the parameters, and for the type former of tree, I have to pass in the parameters to the description, and I also have to sort of take these two arguments and turn them into a pair. And this is also true with the vectors. Like, we can't just say, mu vecti. We have to say mu vecti A, where we kind of know about what this A actually means. And what we want instead is we want some single description, which I call R, because it's going to be a record. Sort of the long story short is we can create a first-class notion of a telescope used to encode the parameters and indices, as well as the constructor arguments. Turn that into a data record, which stores the parameters, the indices, and the constructors. And now instead of having descriptions as our arguments for our dependent derived type theory functions, we can, after we do sort of the same currying and uncurrying at the telescope level, then we can create a generic type former that just curries the constructor arguments, curries the parameters, curries the indices, and then forms using the fixed point. Yeah. So the summary is that we can, if we make the constructor tags and the parameters and the indices and the constructor definitions all explicit codes, then we can sort of reveal type theory as a DSL. And doing that basically involves currying arguments, implicitly supplying index proofs, and implicitly supplying unit values in the case of the telescopes, which I couldn't really talk about. And we might also want to do other things, like none of these things had like implicit arguments in the data type definitions. So we might also add to this list changing implicit arguments to explicit arguments. And this is implemented in a language I'm working on called Spire. So if you declare a data type like vectors here, then it actually elaborates into these helpers, so the ing and the elim and the form and everything. So you can check that out.
As a discussant for this work, I would like to add some words for this topic. I played a little bit with the code that was accessible, and in fact it works like some magic thing, because very complex definitions of this description-based encodings is in fact hidden inside a very clear interface of which allows you to, in generic way, to define your constructors like it was shown. But at the same time, when you try to figure out how to just understand how it works, usually in Agda, it's in interactive mode, in Emacs, for example, you usually make a hole somewhere and then using just requesting Agda to show you the types of the arguments of this hole and the context environment, and then you usually can figure out what's going on, how it works. But in this particular case, all these definitions in just page size definitions, so it's just hard to understand how it works, but it actually works, and a couple of theorems was proved in in the code and they are just type check. So it's correct. So my question that I want to raise is what kind of tool support is necessary, because this is DSL, and usually if the DSL is embedded, it's a common problem for all embedded DSLs. It's some tool support from the compiler, from interactive environment. So in this particular case, I feel like maybe some generic programming technique necessary for tooling support, because it's dependently typed language which we embed our DSL. So any ideas maybe, and what is your thoughts about how to improve tooling support in this particular context?
Yeah, so yeah, there are two major problems that you mentioned. Like, one is that, you know, if you're looking at these interactive, if you're looking at these types interactively, then they sort of expand into these monster, you know, encoded definitions. And then the other one is if you want to do something like a case split in AGDA, then you're actually going to be case splitting on the primitives instead of case splitting on sort of the higher type, the higher level types that you think that you're encoding. And yeah, so I think what you're sort of suggesting in terms of writing more generic functions to expose to the interactive, you know, either Emacs mode in AGDA or whatever your editor is, sort of generic functions that, you know, allow you to do something like a case split, right? So I'm actually working on this for like the language that I'm working on, Spire, to basically what I want to do, like kind of the whole point of this research is to have a core type theory and do as much of the high level stuff in it as possible in the core type theory and sort of bootstrap itself. And that's why I have like, you know, this generic type former and eliminator and constructor and everything. And another thing that you could have is a generic like case split, right? And you can't do that completely within the type theory because, so the way that you would do that is like there's previous work by basically Connor McBride's thesis was translating pattern matching into eliminators. And you could do something like that as a generic program, but not completely in type theory because it relies on knowing if certain arguments are variables instead of values, right? And within the type theory, you can't distinguish a variable from an actual value. The type theory just gets stuck if it's a variable or a neutral term in general. So one thing that might be interesting is to sort of take a MTAP approach where you can write as much as possible within like the vanilla type theory that is not able to distinguish certain things like what is a variable and what is not a variable, and then use those pieces within MTAP, which is a library in Coq for doing tactics within the same language that you're programming with, and allows you to do things like unify variables and terms. And I think this is an interesting approach to be able to sort of bootstrap these user interface problems, and you can do as much as you can within the type theory, and then have a little bit of extra help in sort of the tactic language. And it's also very related. This is more or less what Matthew Sasso did in this Coq equations paper, which implemented compilation of dependent pattern matching into Coq eliminators using tactics, but it would just be sort of like Coq equations with MTAP instead of LTAP, and these like generic helpers for the description primitives in closed type theory instead of using Coq's open type theory. So that's kind of where I'm going with that.
So I think we have maybe two questions.
Hopefully, really quick one. You mentioned bootstrapping levitation. I was just wondering, maybe it should be obvious, but how much of the embedding that you described here is self-representing? Is there a desk of desk?
Okay, so yeah, within the original levitation paper, they did sort of do this sort of thing where the descriptions were actually represented using a description and a fixed point, and the meta theory kind of plays this clever trick to make that not impredicative. And I'm not doing any of that here. So the good thing about descriptions in general is levitation, even though it introduced this concept, is completely separate from the technique of levitation. So it just amounts to, like, instead of having what you save with levitation is having like a lim. You don't have to have a lim desc, because you can have the primitive in on, which is the eliminator for all the fixed points. So in my language, you just have one extra eliminator, which is lim desc, and it just the core language is like one eliminator bigger, but the meta theory is significantly simpler.
Yeah, that's the last question. Okay. Thank you.